Colligative properties have another effect on physical properties, and that's freezing point and boiling point. So the lowered vapor pressure that we see in solutions versus just the pure solvent will actually result in lowering the freezing point and increasing the boiling point of a compound. What's happening as that vapor pressure decreases, it's going to require more energy to actually boil this liquid to bring it that vapor pressure up to atmospheric pressure. And so we see that boiling point temperature increase on our phase diagram. What we see actually is it's like the line for our evaporation phase change and our freezing phase change comes down. So we see our triple point shift down to a lower temperature and a lower pressure. And we see our boiling curve, our evaporation curve come down with that, as well as our freezing point. And so the effect of that curve shifting down is that we see our boiling point here has shifted to here. It's actually increased in temperature at the same pressure. And at the same pressure, we see our freezing point decrease down here. Um, and this is all from solute particles taking up space in the solvent and disrupting those solvent-solvent interactions and creating new ones, solvent-solute interactions. So we can actually quantify this. So I can decide what is the actual freezing point of a solution versus its pure substance with a pretty simple equation. For a freezing point, that change in temperature of the freezing point is going to be equal to the Van Hoff factor times the molality times a constant that we call Kf for freezing. And we have Kb for boiling. The units for this constant are going to be degrees Celsius per molality. So, and it's going to be different for different solvents. And what you're doing is you're looking up that Kf for the solvent in the solution. So here's an example. Here's the constants for water. So the Kf for water is equal to 1.86 degrees Celsius per molal. And our Kb is actually smaller. So there's less of a change to the boiling point of our water than there is to our freezing point. This is 0.512 degrees Celsius per molal. And remember, we're very specifically only using molality here because we're talking about differences in temperature. So as the temperature of our solution changes, so does that density of our solvent or solute if it's a non-volatile solute. So we're going to make sure that we use temperature independent concentration units. And the only one we have for that is molality. So that's always going to be our moles of our solute on top and kilograms of our solvent on the bottom of our fraction. And we take advantage of this colligative property a fair amount. So it's winter now, and as snow or ice comes, a common tactic in the city is to put salt on the roads. It's trying to create a solution with the ice, the water in the ice, that will have a lower freezing point by introducing a solute. And so they're trying to bring that freezing point to a lower temperature, so it's less likely that ice will form at 0 degrees. Now, this is a useful colligative property, and we take advantage of it in winters when it's really cold out and ice starts to form on the roads. The city will go out and spread salt onto the roads. And what we're doing when we put salt on roads or sidewalks in the winter is we're trying to form a solution between the sodium chloride and the water that's freezing. And when they mix, then it's going to lower the freezing point. So water won't freeze at 0 degrees Celsius, but at a temperature that's below that. So if our temperatures around us aren't actually too far below zero, less ice will actually be able to freeze, making our roads and our sidewalks safer to travel on.